Cycles. They are the fundamental idea of trigonometry. Every confusing trig identity and relationship can simply be boiled down to the smallest idea. Cycles are everywhere, in electric circuits, swinging motion, day and night times, and other repeating patterns found in the world. The area of trigonometry simply tries to transform these abstract ideas of cycles into a mathematical world and landscape. But that is a difficult question to solve. How do we take an abstract idea like a cycle and transform it to a world of numbers? Well, the answer to that is seemingly simple. We measure. We measure a point on the circle and simply graph it and we'll see what happens. That's the joy of math, trying to understand different phenomenon by looking at them through different angles and scopes. We can overlay our cycle on top of a simple coordinate plane, with the radius of the cycle being 1. This is because we are measuring just a normal abstract cycle. The radius could be any other number for all we care. It could be 3 pi squared root of 2 or anything else. We're just going to use 1 for simplicity. Now the key insight for measuring a cycle is what we measure in relation to. We need to figure out what makes a point unique from every other point in the circle. This different aspect for each point on the circle is simply the angle from the center. This angle is unique for every different point on the circle and can be used to differentiate between points. If you want another way of approaching it, we can think of measuring in relation with time. As a cycle moves forward with time, we measure the position of the point as it will be different from the position previously. Now this is a little unrigorous, but it can help with reasoning and learning this abstract topic. We can graph the x-coordinate for each angle on the cycle. For angles 0, 45, 90, 135, 180, 225, 270, 315, and finally 360. Notice how a pattern is forming on the graph. If we did this for an infinite number of angles, you could imagine the dots connecting themselves to form a smooth line. We can then do the exact same thing for the y-coordinate, but now instead of graphing the x-coordinate of the point, we're now graphing the y-coordinate for each angle. And if we did this for an infinite amount of angles, we can again see the dots connecting themselves to form a smooth curve. It turns out these curves have a name in trigonometry. The first one we measured, the x-coordinate, is called a cosine curve, and the second is a sine curve. These two are functions of angle. That means where they input an angle and they output the position where that point is on the circle. For example, for the x-coordinate, if we inputted 45 degrees, we get this specific point as the x-coordinate, which is the exact value for cosine of that angle. And the same thing for the sine of 90 degrees. That just means at an angle of 90 degrees, what is the y-coordinate of this point on the circle? And that y-coordinate is just 1. Now there is a really great visualization on Wikipedia of this trait of sine and cosine, where you can clearly see how the angle points to a specific point on a sine and cosine curve. It should be added that other trigonometric functions that you may have heard of, such as tangent, are just constructed from sine and cosine. Tangent is defined to be the relationship of a specific angle with the y point of that angle divided by the x point of that angle. So for example, the tangent of 180 degrees. We would just take the sine of that angle, which is the y point at 180 degrees, divided by the x point at 180 degrees. And the y point at 180 degrees is 0, and the x point is -1. So it will just equal out to be 0 divided by -1, which is just 0. So then we know for a fact that the tangent of 180 degrees is in fact 0. This is similar to almost all of trigonometry. It can be related back to relationships between sine and cosine that are just at the core of trigonometry. Now, when I was learning trigonometry, I was extremely confused about these random functions that seemingly came out of nowhere that we had to use from then on. This video's purpose was to portray these equations in reality in order to give them a more intuitive meaning, more grounded in reality.